In this fourth grade unit, students use general methods of increasing abstraction and efficiency to multiply multi-digit whole numbers, including up to 4-digit by 1-digit numbers, as well as 2-digit numbers. In this video, we'll take a look at 3 anchor tasks that show how students develop that understanding and use it in increasingly efficient ways throughout the unit. At the beginning of Topic B, students start with easier computational cases, like 2-digit by 1-digit multiplication, and use more pictorial and representational methods, like an area model, to solve. Throughout the topic, they'll progress to more challenging computational cases, like 4-digit by 1-digit multiplication, and use increasingly efficient methods, like algorithms, to solve. Topic C follows a similar, though abbreviated, progression. Let's take a look at a task from early in this series, Lesson 8, Anchor Task 2, to see how students begin this journey. As you solve, consider how the area model is a helpful pictorial representation, and notice its connections to the vertical written method in Part B. In this task, students look at 2 ways to multiply 746 times 8. In Part A, they use an area model to compute, finding the area of a rectangle with a length of 8 and a width of 746 broken into its place value units. In other words, they compute 746 times 8 as the quantity 700 plus 40 plus 6 times 8, which, because of the distributive property, can be thought of as 700 times 8 plus 40 times 8 plus 6 times 8. Each of these partial products corresponds with the areas of the subregions in the area model. They calculate 700 times 8 by calculating 7 times 8 times 100, or 56 times 100, or 5,600. Similarly, they find 40 times 8 to be 320, and 6 times 8 to be 48. Lastly, students must add the areas of each of these regions together to find the total area of the figure, which is 5,968. In Part B, students are introduced to the partial products algorithm for the first time. They notice that 5,600 corresponds with the leftmost area in their diagram, and thus represents the computation 700 times 8. Similarly, 320 corresponds with a computation in the middle section of the area model, representing the product of 40 and 8. Lastly, by the same logic, the final partial product corresponds with the area 6 times 8. By drawing connections between these different methods, students can rely on representational strategies to make sense of more abstract ones. Notice that Ayana computed her partial products starting with the largest place first and moving to smaller places, which many students might prefer since it more closely resembles how they compute in their area model. Computing from left to right is equally viable to computing from right to left when using the partial products algorithm. But we'll see in future anchor tasks that computing from right to left is necessary when using the standard algorithm. Throughout the rest of Topic B, students work on increasingly complex computations with increasingly efficient and abstract methods. In Topic C, they follow a similar progression with 2-digit by 2-digit multiplication. Take a look at Lesson 14, Anchor Task 2, to see how the area model and partial products algorithm can be modified for this new computational case. Similar to Anchor Task 2 from Lesson 8, students look at 2 ways to multiply 31 times 23. In Part A, they use an area model to compute, decomposing each factor into its place value units. Then, they find the area of each of the 4 subsections and add them together. This corresponds to the use of the distributive property multiple times to find each partial product. In other words, 31 times 23 is equal to 31 times the quantity 20 plus 3, which is equal to 31 times 20 plus 31 times 3. Using the distributive property again for each of these terms, we get 30 times 20 plus 1 times 20, plus 30 times 3 plus 1 times 3. Notice how each of these terms is represented in the area model. In Part B, students see the computation written vertically in the partial products algorithm. They see how each partial product corresponds with the area of each section of the area model, helping them make connections between methods to encourage them to use the most efficient one that makes sense to them. Note how when the partial products are added together, 9 tens plus 2 tens results in 11 tens, or 110. The regrouped hundred is written on the equal bar, as it is for any addition problem as they saw in Unit 1 when they learned to fluently add multi-digit numbers. Also note that this way of writing the partial products differs from the partial products in Lesson 8, Anchor Task 2, since the partial products are written in increasing order here, which will help prepare them for their introduction to the standard algorithm in the next lesson. The total product here, 713, matches the product as computed with the area model, helping students see that both methods are valid, but with different levels of efficiency. In Lesson 15, students draw connections between the area model, partial products algorithm, and standard algorithm. First, they see in Anchor Task 1 that area models for 2-digit by 2-digit multiplication can be partitioned in two different ways. Then, in Anchor Task 2, students will compare these area models to the partial product algorithm and the standard algorithm. Take a moment to solve this task, thinking about the connections between these written methods and the area models just shown, as well as the connections between these written methods themselves. Similar to Lesson 14, Anchor Task 2 above, the 4 sections of Joy's area model connect to the 4 partial products of Calculation A. Sophia's area model, however, was combined so that there were just 2 sections, one corresponding to 13 times 60, and the other corresponding to 13 times 2. These connect to the 2 partial products in Calculation B, written in increasing order. Also note the connections between the partial products algorithm and the standard algorithm. You can see how the first 2 partial products in Calculation A add together to give the first partial product in Calculation B, and similarly with the second 2 partial products in Calculation A corresponding to the second partial product in Calculation B. Let's take a closer look at how the standard algorithm in Calculation B was computed by walking through it step by step. First, to find the first partial product of 13 times 2, the student multiplied 3 times 2, which is 6, writing the 6 below the line in the ones place, then multiplying 1 10 by 2, which is 2 tens, and writing the 2 below the line in the tens place. For the second partial product of 13 times 60, the student again started with the smallest place first, multiplying 3 times 6 tens to get 18 tens, or 180. They wrote the 0 in the ones place and the 8 in the tens place. The regrouped 100 is written as a smaller digit above the hundreds place of that second partial product. This regrouped unit is written above its corresponding place in the solution as opposed to above the computation for a few reasons. First, it makes it easier to write these digits in their usual order, the 1 first and then the 8. It also means that the 2 digits, 1 and 8, are recorded near each other, visually suggesting where they came from. Further, if instead students wrote these newly composed units above the 13, this would mean that the 100 in 180 would be written above the 110 in the first factor. Writing the 1 here goes against the convention that students are used to. A digit in the tens place represents tens, not hundreds. Lastly, it makes it easier for students to work from top to bottom in their next computation, multiplying 110 times 6 tens to get 6 hundreds, then adding the previously composed 100 to get 7 hundreds. The 100 is crossed off so that it's not double counted later, and the 700s are recorded in the hundreds place of the second partial product. This second partial product helps to show why we multiply starting with the smallest place first in the standard algorithm. If in the second partial product we instead computed 110 times 6 tens to get 6 hundreds, then 3 ones times 6 tens to get 180, we'd have to account for the regrouped 100 after we had already computed in the hundreds place, which would be an inefficient and confusing process. Finally, after computing and recording their partial products as shown, they add those partial products together to find the total product. Remember that students are not expected to be fluent with the standard algorithm for multiplication in 4th grade, but this extensive work with general methods that increase in efficiency, including an exposure to the standard algorithm, will help prepare them for that 5th grade work. In the next big idea of this unit, we'll look at how students solve multiplicative comparison word problems, including some that rely on this newly acquired understanding of multi-digit multiplication.